Hi guys. This is a video that I put together to show a quick little demo of using object-oriented programming techniques with the Ada programming language. I know a lot of people are familiar with seeing object-oriented programming in more commonly used languages like C++ or Java or Python or a lot of others really. Most people don't see Ada very much because it's kind of a specialty language that's really just used for safety-critical real-time control systems. But I love the Ada programming language because it gave me a great career doing embedded software for aerospace systems. And it's really a nice language because it has a nice clean syntax, but it also gives you the same level of low-level machine operation access that you get with a language like C. So I just wanted to do this demo here to show how object-oriented programming techniques are used in Ada. And I'm assuming that people watching this video will already be familiar with the basics of object-oriented programming and how it's used in other languages. So I'm not going to spend a lot of time going over that, just kind of give a quick introduction to it here. The idea here is to describe a problem in terms of objects, which are self-contained in terms of control and data during both the design and the implementation. And communication should be limited between objects and only through a well-defined interface. So this design approach is good for problems where you'll be working with several different objects that all have things in common. It gives you a consistent way of dealing with different objects in terms of what they have in common. So for a sample problem to put together, I wanted to create a program that you can use for a basic level of problems in computational physics involving particle motion in a plane. So for my sample requirements here, we're going to develop software to support problems involving particle motion in a plane. The software must be designed to support different types of two-dimensional particle motion problems, including projectile motion, both without and with air resistance, and also circular motion with a constant angular velocity. So each particle must have the following attributes: mass, a position in 2 dimensions as a function of time, a timer to track the current time, a specified final time, and a specified time increment. So the basic idea is we're going to create something that is a particle, and it's going to be moving from a start time to an end time. And at a specified time increment, we want to be able to check its position throughout its movement so that at the end, we have a file with all of the position data as it moves through its movement so we can do our analysis on the data. So to have all of these attributes for a particle, here's what our class diagram starts to look like. We want to define our problem in terms of the data that we're going to work with and the operations that we're going to do with the data. So for a particle, we're going to have x and y values. The double here, my design tool here is using the notation that's common for C and C++. So this is just a double precision floating point number. I'll be doing it in Ada, where that same type is called long float, for a floating point number that has a longer precision than a regular floating point number. But anyway, we'll have an x and y position, we'll have a mass, we'll have a time, which represents the current time, time final, which represents where it is at the end of its movement, and then we'll have a delta time, which is the time increment that we're going to use. So in Ada, to have all of these contained in one item, we'll use a record. This is comparable to a struct in C or C++. In Ada, they just call it a record. So we'll say type particle is record, and then we list out all of our components here. This way we can have an object that's of this type, and we can refer to it by name and have access to all the different components here. But since we want to do it in an object-oriented way, to tell the compiler that we want to derive other types from this, we add a tag to our record. So we'll say type particle is a tagged record. And this tells the compiler that we're going to derive other types from this, and we want them to all have these characteristics. So this is the data that we're going to work with, and we also need to define the operations that we want to do on our data. So the particle class shall provide the following operations: initialize a particle, functions to return the mass, x and y position, and the current time, a function to increment the time and recalculate the position values, a Boolean function to indicate if the particle has reached its final time. We want a function to print the current time, x position, and y position, and a function to prompt the user for initialization data values. So something to mention up here. A typical concept with object-oriented programming is to have a constructor and a destructor method that you use to allocate the RAM and the resources needed for each object. In Ada, you only need a constructor function if your object includes something that requires dynamic memory allocation. And in this application, we don't need that, so there's no need for an actual constructor to allocate the RAM. We just need to give it initialization values to start with. So we'll have an initialization function, and then after we do that, we can run through it. Also, I've got functions here to return the mass and the position and the time, but I'm also wanting one here that will just print the current time, x position, and y position to the standard output. And I'm doing it this way because for some applications, you'll want to check these components individually at various times. But for the main use of this one, what I have in mind is, as it cycles through its movement, we're going to print the current time and the position in columns so that at the end we'll have this output data file with columns of data that we can use to do our analysis on. So to add these operations to our class, we have our class diagram here with a particle that has these attributes. And then here's the list of the operations that we can do with it. And as we go through and derive different classes from this particle, all of them will have these operations so that we can use them all in a consistent way. So to see how this looks in my Ada program, in C or C++, you would have a header file that doesn't contain any executable code, but just contains the specifications for what types of data you're defining and prototypes for the functions that you're going to use so that the person using it can see what the data is and what functions you have and how you can use them. In Ada, that's called a package spec. So I have my package spec for a particle here. This is what the user will be looking at to see how to use a particle. So I put lots of comments in here to describe how everything works. But my class definition is down here with this type particle is tagged record. And then I list out all the different components. They're all of type long float. So then anything that is a type particle will have these components. And then I give my specifications for all of my procedures here to initialize the particle and to get the mass and the current position and time. I have a function completed. The base class version of completed will return true when the current time has exceeded the final time. And then here we have a procedure to increment the time. In C or C++, everything is a function with a return value. And if it's not going to return anything, you just use void for the return value. But in Ada, there's a distinction between a function that returns a value, like this function completed that returns a Boolean, or a procedure that has no return value. In this case, it will just do the work and it will change the particle as it does its work. So then I have one to put the data and to get the initialization data. And then I added at the bottom an exception called invalid delta time. Because I have a requirement up here. Where did I describe that? Basically, we're going to initialize our particle with a specified final time and a delta time to increment by. So if the user specifies a delta time that's greater than the final time, that doesn't make sense. So in that case, we just want to raise an exception and exit. So before I take a look at the particle types package body that gives the implementation of all these functions, I want to show what the program using it looks like. We want it to be as simple as possible to use it. So here, all I do is declare something that's a particle. Then I prompt the user for the initialization data. Then I have my while not completed loop, increment the time and put the data, end loop. So it will cycle through this until completed returns true. And that's all there is to using it. And in this case, we're not going to actually use this particle, because we mean this just to be the top level parent class that we're going to derive other particle types from. And you can use the word abstract to show that this record isn't to be used by itself, but is just to be used as a parent class to derive others from. Instead, for this example, I went ahead and made it usable just so that we can see the common way that we're going to work with all types of this class. So in my package body, where I give the implementation of the different procedures, we have our initialize thing. It checks to see if the time is greater than if the time delta is greater than the total time, it'll raise this invalid delta time. And if not, it'll just go through here and add initialization data. The work is done in this increment time procedure. And in this case, this isn't a real example because it's just going to be the top level parent class. So I just added a basic thing here. If it's not completed, it increments the time, and then it just adds a number to the x and y values. So this won't be anything real, but it's just to show an example of how we're going to use it. Then I have my put data procedure here. If it's the first pass through, it'll print a little column heading here to show that I'm printing the time, the x and the y values. And then I'll go through and I'll put each of these. Since I'm using floating point numbers, I want to tell it that before the decimal point, I'm going to have 2 digits. And after the decimal point, I want to have 4 digits. And then have a 0 exponent. And then I have a procedure that will prompt the user to enter values for the time and the time increment. And then it calls initialize particle. So that's all there is to the implementation. So that by having it all in this package, my using program can be really simple like this. So as you go through the program, it will prompt you for initialization data. So if I say test particle, it'll prompt me for a total time. I'll say 10.0. A time increment, I'll say 0.01. And then it just prints all of my output data. And I can see at the top here, I've got my headings for time, the x value, and the y value. And this is just as the particle moves through its process here. So to work with it, what I want to do is put all of my output data into a file. So let's say test particle. I've got my input data put into this input data file, p1in.dat. And I'm going to tell it to put the output into a p1out.dat file. So then I look at my output file. I've got all my data here. So to look at the results, I'm going to use the GNU plot tool to plot my data. So I'm going to tell it to plot this p1out.dat file. I want to use columns 2 and 3. Column 1 is the time, and then you have the x and the y. I want to plot the x versus the y position. So I'm going to tell it to use columns 2 and 3, and then with points. Point type 0 is just a dot, so that's kind of the cleanest way to plot this data. So as you can see, it's just a straight line. This one isn't doing anything interesting, but this is just the example of how we're going to work with objects of type particle. So what we want to do is derive different types from this particle class that all have their own characteristics, but also share all the characteristics of this parent class particle. So we're going to start with circular motion. The circle class shall inherit all characteristics of a particle and shall add items needed for uniform circular motion with a constant angular velocity. This will require adding data for the center x and y, the radius, the starting angle, and the angular velocity value. X and y components of the angular velocity will also be needed. The circle will require different operations for initializing a circle, as well as for increment time and get init data. All other operations can be reused from the parent class particle. So I look at my class diagram for this. We started with our top-level parent class of a particle with all this data and these operations, and then we derive from it a circle. And this line here connecting them shows that circle is derived from particle. And in object-oriented terminology, This is the is-a relationship that shows that anything that is a circle is a particle, which means we can work with it using all of these methods that are common to all particles. But it also includes its own data and operations. So to take a closer look at this, our circle is a particle, and we're adding theta for the angle, omega for the angular velocity. We'll have x and y components of the velocity, r for a radius, and then the center x and y positions. And it will have its own initialized circle, increment time, and get init data procedures. So to take a look at how we implement that, we started with particle types here where we defined our type particle as a tagged record. So for our circle that we're deriving from this, we're going to say type circle is a new particle with a record, and then we add all the additional data items here. And then it has its own initialized circle routine with all the additional data items. And then it has an increment time and a get init data. So that's all there is to defining the type that we derive from the particle. So then again, the work is done here in our package body. The initialize function will just get it'll initialize all the data items that are unique to a circle, and then it will call the top level initialize particle method for the rest. And the work gets done here in increment time. If it's not completed, we add the time increment to the total time. Then we compute the new angle, the x and y values of the particle, and the x and y components of the velocity. Then for our get init data routine, we prompt the user for all the additional data, and then we just call the initialize routine. So then we get to the program that uses it. It should look exactly the same as using the original particle. So in my test particle here, we just define a data item that's a particle. Then we get the init data. We have our while not completed loop where we increment the time and put the data. The one that uses the circle looks exactly the same, except that here we're just declaring our data to be type circle. Then we get the init data, while not completed loop, increment time, put the data. So it's used in the same way that other particles are used. So I can run test circle here. I'll get my initialization values from p2 in.dat, and I will put the output to a p2 out.dat. So my output looks basically the same. I have prompting the user for each of the values, and then it just prints the columns of data. So when I come down here, I can look at this the same way, and I just tell it to plot from the p2 out.dat file. Here we can see I've got my circle. This is the x and the y position as it moves through its entire movement. And it keeps moving through until the time reaches the final time, because that's how we've defined it in here. For increment time, the first thing it does is call completed, and completed is reused from the original class, where all it does is here it is, it just checks to see if the time has exceeded the final time. So then we want to derive another different type from this, because we want to also look at particle motion, or projectile motion, and we want one that doesn't include air resistance, and then another one that does. So class projectile shall inherit all characteristics of a particle, and it shall add items needed for projectile launched from flat ground. The projectile will be launched at a specified angle from the horizontal, with a specified initial velocity, and will continue until it lands on flat ground, so the y value just returns to the initial y value. Air resistance will not be included, because we'll be adding that later. So the projectile will require different operations for initializing a projectile, as well as for increment time and get init data. A new completed function will be needed, as the projectile is finished when it lands at the same y value it started from. All other operations can be reused from the parent class particle. So then we'll also have a projectile air. It will inherit all characteristics of a projectile, but it will also add a component for air resistance. The value 5.0 is used for air resistance. This is kind of a simplified way of getting started looking at air resistance. It's really more complicated than that, but this is kind of a typical way to first get used to how you can add air resistance to your projectile motion problem. So this will require a separate increment time procedure, and all the others can be reused from the projectile class. So we look at the class diagrams we create for these. We've got a projectile, we're adding our angle and our initial velocity, and we're adding these other components to initialize a projectile, completed increment time, and get init data. And then from this, we're deriving our air projectile with our little is-a relationship here, showing that a projectile air is a projectile, and it also adds k for the air resistance and its own increment time procedure. So in the end, our total class diagram looks like this, where we've got our parent class particle with this data, these characteristics. And we've derived from it a circle, and now we've derived from that a projectile, and then from this projectile, we've derived the projectile air. So I come back to take a look at this. My spec for projectiles looks about the same. We're saying type projectile is a new particle with a record. We're adding a few more data items, and we're giving it its own initialize, completed, increment time, and get init data. Then here for another level, we're adding type projectile air is a new projectile with a record, and we're adding our k here. And then we have a couple new exceptions that we've added, invalid angle and invalid velocity. So then again, when we use it, it looks the same. Our test circle procedure looked like this. We declared a circle, get init data, and have our while not completed loop. To test the projectile, it looks the same again, except that we have a projectile. And then again, we've got the same thing for a projectile air. This kind of shows how, even though we have multiple levels of inheritance, we have a common way of working with all of them. So if I want to test this one, I can say test projectile. My input data will come from p3 in.dat. And I'll put my output data into p3 out.dat. Then I can do the same thing with the projectile air. I'll read the same input data, and I'll put it into p3a out. So now to show that data, I'll just change this to p3 out. So here it prints our data, and this is not a picture of what the trajectory looks like. This is just plotting the x position against the y position. And the scale is different. You can see that here it goes a little bit past 10, but up here it only goes up to about 2.5. That's because GNU plot is trying to plot the data to fit it to the size of the window. But we can tell it to make it to scale too if we want. I'll show that in a minute. But first I want to add the other one. So if I say replot, it will add the new plot to the same file, and I called this p3a.out. So here we can see it's added my plot of the same projectile with the air resistance. In this case, it used all the same starting values, but just added air resistance, so it goes a much shorter distance. That's kind of what we expect. So if I want to make the drawing to scale, I can tell it what size to use. So I'm going to say 0 to 12 for the x and 0 to 12 for the y. Now we have a drawing to scale. We can see that we've got the right angle here. So then I can go through again and replot my the one with air resistance. And this shows kind of how the two of them look together. And then if I want to, I can go back and add my circle again. I say replot to use the same window. P2. So here it shows that we've got all three of them plotted together the same way, because we have a common way of working with all of our different objects. Because here they're all the same thing. In the end, they all have their own characteristics, but they're all just different versions of a particle. So we have a common way of working with all of them. So that's kind of my basic demo of object-oriented techniques using Ada. So thanks for watching my video.